Hello guys, welcome back to Math Without Tears. In this video we're going to look at differential equations. In particular, we're going to be solving differential equations called homogeneous differential equations. Remember, we have talked about homogeneous differential equations in the past videos. If you can put a differential equation in the form dy by dx equal to f of y over x, or a function of xy divided by another function of xy, we can call that a homogeneous differential equation. In that case, we simplify the solution by defining y over x to be v, and then we solve for dy by dx. Now let's apply that here and see how we can resolve this differential equation. Now I'm going to go ahead and first try to create y over x. And I can easily do that by factoring out x squared, because there's no way I can divide in here as I have the square root sign. Now, this implies y minus x dy by dx is equal to the square root of x squared. Remember, I want to factor out x squared. So I'll have y squared divided by x squared minus 1, all that square root. And this implies that y minus x dy by dx is equal to, now I can separate this as the square root of x squared times the square root of y squared over x squared minus 1. In that case, the square root of x squared will give me x times the square root of y squared divided by x squared minus 1. Now I can divide both sides by x, and this is going to give us y over x minus, the x here cancels out because I'm dividing each term by x, equal to the square root of, what I can do here is I can put y over x, all that squared minus 1. This is for me to easily see that I can define my v equal to y over x, or my y equal to vx, wherein dy by dx will be equal to, the product rule applies. I keep one constant and I differentiate, so I keep v constant, I differentiate x, that gives me dx by dx, that gives me 1, plus I keep x constant and I differentiate v, which is dv by dx. Now I have my dy by dx. I can substitute in this equation and continue the solution. So let's go ahead and substitute. Instead of y over x, I'll have v minus, instead of dy by dx, I'll have v plus x dv by dx equal to the square root of v squared minus 1. So opening the parentheses, this cancel out already. And I'm going to have negative x dv by dx equal to square root of v squared minus 1. Now I can separate variables here easily. I can easily separate variables, and I'll have negative x dv divided by square root of v squared minus 1 equal to dx. And I'll have negative dx over x. Now I have separated the variables. I can apply integral signs on both sides, and I'll have the integral of 1 over the square root of v squared minus 1 dv equal to the integral of negative 1 over x dx plus k. Right? Now this implies the integral of 1 divided by the square root of v squared minus 1 dv is equal to, remember, each time we're integrating 1 over a function times the differential of that function, the answer is always leaving the absolute value of that function plus k. Now we are left to integrate the left-hand side. Now, the left-hand side, if you've not done hyperbolic functions, it's going to be very complicated for you to integrate the left-hand side because you are looking for an expression in which you can find v squared minus 1. You can find something like v squared minus 1. So, let's move on the next side. Let's consider the integral of 1 divided by v squared minus 1 dv. From hyperbolic functions, we know that cos squared v minus sin squared v equal 1. So, of course, this implies that sin squared v equal to cos squared v minus 1. So, I can have cos squared v minus 1. So, because this is v and I'm putting this in terms of v, let's change this to x or to some alpha. Just not to get things mixed up, let's put this as alpha. All right? Now, we can say let v be equal to cos alpha. So, let v equal to cos alpha. If v is cos alpha, we can find dv because we can now substitute this and keep integrating without considering the differential of v. So dv is going to be, whenever you differentiate cos alpha, you're going to have sin alpha. Now, let's go ahead and substitute. This integral will become integral 1 divided by square root of cos squared alpha minus 1 times sin alpha d alpha. And this is equal to, we know that cos squared alpha minus 1 is giving us sin squared alpha. So this is integral of 1 over the square root of sin squared alpha times sin alpha over 1 d alpha. Of course, these squares will cancel and I will have the integral of sin alpha divided by sin alpha d alpha. This is equal to the integral of d alpha, which is equal to alpha plus k. Without hyperbolic function, this integral would have been very difficult. So I'm not going to talk much about hyperbolic functions right now. We're going to make another video for hyperbolic functions. But right now, we are still on differential equations. If v equal to cos alpha, what does that mean? It means alpha is equal to cos inverse of v. In hyperbolic functions, cos inverse of v is ln the absolute value of v plus the square root of v squared minus 1. So it means I can substitute. I can go ahead and substitute integral of 1 over v squared, that is this integral, 1 over 1 minus, that's v squared minus 1 dv is equal to ln the absolute value of v plus the square root of v squared minus 1 plus k. But this integral is equal to negative ln the absolute value of x plus k. Ln the absolute value of v plus square root of v squared minus 1 plus k equal to, now that we use k right here, we can call this k prime. Now this is going to be equal to negative ln the absolute value of x plus k. We can combine the k's together and we have a c. Ln the absolute value of v plus square root of v squared minus 1 or square root should be equal to negative ln the absolute value of x plus a constant c, where c is k minus k prime. Again, we can combine these two using the laws of logarithm. We can bring this way, put them together. It's going to give us just ln the absolute value of x times all of these. But doing all of that, we are just making it to look good. But this is already the n and this is already the general solution. But we have to note that our function was given in terms of x and y and not in terms of v. So we have to go back and substitute v, which is y over x. So this is going to be ln the absolute value of y over x plus square root of v over y over x all squared minus 1 equal to negative ln the absolute value of x plus c. This is the solution of the differential equation.